If not, then we're going to go ahead and get into today's information. So let's look at, oh, I don't know. We'll go with that problem. I don't think I did that problem. What mass of hydrogen can be produced if 9.43 grams of arsenic reacts with excess sodium hydroxide according to the reaction two arsenic plus 6 sodium hydroxides goes to make 2 sodium arsenides plus 3 hydrogens. Okay. We're going to identify what we were given. We were given 9.43 grams of arsenic. Next, we identify what we want to solve for. We want mass of hydrogen, meaning we want grams of hydrogen. Looking at this, the substances are different, and therefore you're going to need a mole-to-mole ratio, which will come from the balanced chemical equation. According to the balanced chemical equation, 2 moles of arsenic react to give 3 moles of hydrogen. The next thing I'm looking at is I have mass. Anytime I have mass, it means I'm going to need the molar mass. So we look up the molar mass of arsenic. And the molar mass of arsenic is 74.92 grams of arsenic is equal to 1 mole of arsenic. The next thing I realize is I have grams of hydrogen. If I have grams of hydrogen, that means, again, anytime I see grams, it means I need the molar mass. I have 2 hydrogens, NH2, times 1.01, or in other words, the molar mass is 2.02. That's 2.02 grams of hydrogen is equal to 1 mole of hydrogen. Now I'm ready to start this problem. I always start with the information that I was given. So I'm going to start with the 9.43 grams of arsenic. My first conversion factor has to have grams of arsenic because I need it to cancel out, and therefore I'm going to be using the molar mass of arsenic. For the molar mass, the 74.92 grams of arsenic go in the denominator, and the mole of arsenic goes in the numerator. We place the grams of arsenic in the denominator so that the unit and the substance would cancel out. And we're left with moles of arsenic. My next conversion factor has to have moles of arsenic in it, and it has to be a different conversion factor. So I'm going to use the mole to mole ratio. I'm going to place the 2 moles of arsenic in the denominator and the 3 moles of hydrogen in the numerator. The 2 moles of arsenic were placed in the denominator so that the unit and the substance would cancel out, leaving moles of hydrogen. I now have the substance I wanted, but I don't have the unit I want. So now I'm going to use the molar mass of hydrogen to convert that into grams of hydrogen. The mole portion will go into the denominator with the mass portion in the numerator. We place the mole portion in the denominator, so again that the unit and the substance would cancel out, leaving us mass of hydrogen. Because we have the unit we want, we are now ready to solve this problem. And when you key this into the calculator, you get 0.38138 grams of hydrogen. Now we do have to pay attention to significant digits. In our first value, there are 3 significant digits. In the molar mass, the mole portion is an exact quantity, so it has an unlimited number of significant digits, while the mass portion has 4 significant digits. The mole to mole ratio, that is an exact quantity, so the numerator and the denominator have an unlimited number of significant digits. The molar mass of hydrogen, the mass portion has 3 significant digits, and the mole portion is again an exact quantity with an unlimited number of significant digits. Since this is multiplication and division, the answer will have the same number of digits as the measurement with the fewest. The measurement with the fewest had 3 significant digits, so we are going to record this answer to 3 significant digits, and therefore we would record our answer as 0.381 grams of hydrogen. Again, folks, on the exam next Tuesday, you will have one question that is similar to this, where I give you the balanced chemical reaction. The only difference is in that particular question, I also give you the molar masses. But then you're going to have a second question that is similar to this, where you are given the balanced chemical equation, but you got to calculate the molar masses. So you're going to have 2 questions that are similar to this on the exam next Tuesday. Let me give you a problem to work before we move on to molarity. Okay. What mass of carbon dioxide can be produced when 2.34 grams of I-2O5 react with excess carbon monoxide given the balanced chemical equation is I2O5 plus 5CO goes to form 5CO2 plus I2. Now, just so that you know, and in case you don't have your periodic table available, iodine has a mass of 126.9. Carbon has a mass of 12.01, and oxygen has a mass of 16.00. Those are the individual elements' molar masses. Okay. So what we were given was 2.34 moles, 2.34 grams of I-205. We were asked to solve for grams CO2. The first thing I noticed is I-205 and CO2 are different formulas, and therefore I was going to need a mole-to-mole ratio, which I got from the balanced chemical equation. The second thing I noticed is that I was given grams of I-205. Anytime I see grams, it means I need the molar mass. So I calculated the molar mass of I-205, and that's 333.8 grams of I-205 is 1 mole of I-205. I then noticed that I needed grams of CO2. Since I needed grams, again, anytime you see grams, it means you're going to need the molar mass as a conversion factor. So I calculated the molar mass of carbon dioxide, which is 44.01 grams of carbon dioxide is 1 mole of carbon dioxide. Once I had broken down what I was given and what I needed to solve for, I started with what I was given. I was given grams of I-205, so my first conversion factor had to have grams of I-205 in order for the grams of I-205 to cancel out. So I used the molar mass, and it was 1 mole is over 333.8 grams of I-205. Again, the grams of I-205 were placed in the denominator so that the unit and the substance would cancel, leaving moles of I-205. The next conversion factor I needed was going to have moles of I-205 in it, but it had to be a new conversion factor. So that left the mole-to-mole ratio. And the mole-to-mole ratio, I put the 1 mole of I-205 in the denominator and the 5 moles of CO2 in the numerator. We placed the mole of I-205 in the denominator so that the unit and the substance would cancel, and we were left with moles of CO2. But ultimately, we were asked for grams of CO2, and therefore the next conversion factor I needed had to have grams of CO2 in it. So that's when I used the molar mass. From the molar mass, I'd put the 1 mole of CO2 in the denominator so that the unit and the substance would cancel, leaving grams of CO2 in the numerator. And then when you completed the calculation, you should have got 1.54 grams of CO2. And that is to the correct number of significant digits. Yes. How did I get the molar mass? So I-205 says that there are 2 I's and 5 O's, correct? I is 126, I gave it to you, 126.9. And O is 16.00. When you multiply the I together, you get 253. Come on, stop moving. 253.8. When you multiply the oxygen, 16 times 5, you get 80.00. And when you add those together, you get 333.8. And you would do the same type of thing with the CO2.
It's not an issue there, but you're looking at significant digits there before you put it in the problem, right?
If I ask you to calculate just the molar mass, then yes, I'm going to look at significant digits. If I'm asking you to use the molar mass in the problem like we did previously, then I'm not worried about how many significant digits are in the molar mass, because it's always going to be greater than whatever I gave you to begin with. So, and that way I don't have a compounding error due to rounding.
Right. Okay.
Other questions? So only when I when I ask you to calculate molar mass am I going to be
right. It's because you're waiting until the end, right?
Right.
That's the essential.
Right. Okay. It's always at the end of whatever I'm doing. Did that answer your questions where it made sense? Okay. Any other questions? Because if not, we're going to move on. So if you go up to the, first of all, there are 4 common states of matter that you are going to encounter. They include a solid, which we represent with the letter S in parentheses, usually following the formula of the compound. This means that you're going to have mass, because we can measure solid using mass. You will have a pure liquid, and we represent it with a cursive L in order to separate it from a 1, because they look the same when they're typed. So we represent it with a cursive L to make sure that it's obvious. And a lot of times you're going to measure this using volume. We can also talk about gases, which we represent with a lowercase g, again in the parentheses, following the formula of the compound. So for instance, carbon dioxide is typically in gas form. So we would write CO2 gas with the G in parentheses following the CO2 formula. Now, the 4th most common one that you are going to encounter, especially through college chemistry 2 or general chemistry for health sciences, is going to be that of an aqueous solution, which we will represent with a Q in parentheses. What we're going to talk about specifically is this concept of a solution. What is it if we say solution? So what we're going to deal with for the rest of the semester, which is the rest of today and Thursday, is we're going to talk about solutions. Number 1, we're going to talk about what a solution is. Number 2, we're going to talk about how we, let me rephrase, how we describe the concentration of a solution. Then we're going to talk about how to make a solution. From a solid and a liquid. And then lastly, we're going to talk about conversions. Involving concentration. That is going to be the focus of the rest of the semester. or I should say the rest of the new information this semester. So let's begin with this concept of a solution. A solution results from a solute. I'm combining words. Being dissolved in a solvent. In other words, the solution is equal to the solute plus the solvent. The solute is the component dissolved in the solvent. It is typically the minor component of the solution. And it oftentimes is the component that changes state of matter. The solvent is the major component of the solution. For aqueous solutions, which is what we will primarily deal with, the solvent is water. So all I've done right now is describe what a solution is. A solution is a solute plus a solvent. Now, let me give you examples of solutions. The air you're breathing is a solution. Now, technically, it is a solution of gases. The major component, which is the solvent, is nitrogen gas, because the air you're breathing is 78% nitrogen. The oxygen, which our body needs, is a solute, because it's only the air you're breathing is only 21% oxygen. So, as I said, the solute is the minor component, 21%, compared to the solvent, nitrogen, which is 78%. Another example that you would be familiar with is The peroxide that you go to the store and buy. The peroxide that you go to the store and buy is 3% hydrogen peroxide. That solution is made by dissolving liquid hydrogen peroxide in water, and therefore the hydrogen peroxide is the solute and the water is the solvent. 3% is hydrogen peroxide, the other 97% is water. Those are examples of solutions. Another example of a solution is every time you cook, well, most of the time, I can't say every time, most of the time when you're cooking, you add some table salt to water, for example, to boil pasta. Well, when you're adding table salt to the water, you're adding a solute, the table salt, to the solvent, the water. The table salt changed its state of matter. It's no longer going to be a solid that you put in. It visibly changes. So that's another example of a solution. The fact of the matter is if I go upstairs, I'm going to find lots of solutions. So now, how do I describe these solutions? Well, I mean, we could decide. Let's take tea, for example. You steep tea on a stove in a small pot of water, small amount of water. I'm not going to want to drink that tea. That's going to be awfully strong. Usually, we take that steeped tea and we pour it into a pitcher, and then we add more water to it, therefore diluting the steeped tea and making it a weaker solution. But if we describe it strictly by strong or weak, that can mean a lot of things. Let's go back to my table salt example. I can put a little salt in the water. And if I were to taste it, it would be a little bit salty. But if I put too much salt in that water, it's going to taste terrible. But just describing it as weak or strong, that really is not helpful. Because your idea of weak and my idea of weak are going to be two different things. I'm not a big salt person. It doesn't take very much for something to become too salty for me. So your idea of weak and my idea of weak are going to be two different things. So weak and strong, not useful for describing the solute compared to the solvent. So solutions are described by units of concentration. Now, these units of concentration can come in a variety of forms. I actually gave you one, and one form of a unit of concentration is percentage. And that is a unit of concentration that is commonly found in in the medical field. We talk about the percent of peroxide. We talk about the percent of isopropyl alcohol. We talk about the percent of sodium chloride in a drip. So it's a common one that is used. But now in chemistry, a common unit of concentration is molarity. Molarity is represented with a capital M, and it stands for moles of solute over liters of solution. And as I tried to indicate a moment ago, though I did not say it, I tend to shorten the word solution by writing SOLN. So, if I say concentrated hydrochloric acid which is HCl aqueous, is 12 molar. What do I mean? Well, if concentrated hydrochloric acid is 12 molar, what that means is that 12 molar is that it is 12 moles of hydrochloric acid in 1 liter of solution. Concentrated sulfuric acid which is H2SO4 aqueous, is 18 molar. What does that mean? Well, if it's 18 molar, it means that it is 18 moles of H2SO4 in 1 liter of solution. So if I ask you, what does 1.24 molar NaCl mean? You would say what?
1.24 moles of NaCl in 1 liter solution.
That's what you would tell me. You need to be prepared to think this way. You you need to be prepared to think this way, where you can take that capital M molarity and you can break that molarity into its units. The reason you need to be able to think this way is really twofold. Number one, if I am going to make a solution, then I need moles of my solute and I need volume in liters of my solution. But the second reason you need to be able to think this way is because by taking molarity and breaking it into its individual units, what you just did is you created a conversion factor. You created a conversion factor that allows you to go between moles of something and volume of its solution. We are going to look at both of those ideas. And we're going to look at when you got to be able to do which piece. So the first one is going to create a solution from a solid. Let me give you an example. What is the molarity of a solution that is made by dissolving 12.489 grams sodium chloride in enough water to make 250 milliliters of solution. Okay, folks. I asked you for the molarity. The formula for molarity is a constant. The formula for molarity, capital M, is that it is the moles of solute over the liters of solution. Meaning, I need moles solute. Well, how am I going to get to the moles of solute? I am going, what is the solute in this solution? The solute in this solution is this sodium chloride. The solute in this solution is that sodium chloride. So that means I'm going to take 12.489 grams of sodium chloride, and I have got to get that into moles of sodium chloride. How do you convert grams into moles? What is the conversion factor to convert grams into moles?
It's like mole over molar mass.
It's the molar mass. That's the conversion factor. It's always the molar mass. Because anytime you see grams, the conversion factor is the molar mass. So because I saw grams here, I need the molar mass. Which, if you calculate the molar mass, is 58.44 grams of NaCl is equal to 1 mole of NaCl. Remembering that the Na is 22.99 from the periodic table. Cl is 35.45 from the periodic table, and that's how I got the 58.44. So we're going to take this 12.489 grams of NaCl. We're going to use the molar mass of 58.44 grams of NaCl is equal to 1 mole of NaCl in order to convert that into moles of NaCl. And we get 0.21371 moles of NaCl. The next thing I have to deal with is I have to deal with liters of solution. I was given milliliters of solution. How do I convert so I've got to convert 250 milliliters of solution into liters of solution. The conversion factor that's going to allow that to occur is going to be the metric prefix system. Now you can use the metric. I will say I use a slightly different version a lot when I'm dealing with milliliters. And that version that I deal with is that there's 1,000 milliliters in a liter. Or you can write that 1 milliliter is equal to 1 times 10 to the minus 3 liters. You can use whichever one you have memorized. So 250 milliliters, I will convert that into liters. So it is 0.250 liters of solution. Now, looking at it, I have the 2 components for molarity. Because molarity is mole solute over liter solution. So this is going to equal the 0.21371 mole of NaCl divided by 0.250 liters of solution. And you get 0.855 molar NaCl. Now, if I'm recording this according to significant digits, again, for significant digits, the only thing you have to pay attention to is your starting quantities. The 12.489 had 5 significant digits. The 250 milliliters had 2 significant digits. So I'm going to record this as 0.86 molar NaCl, which typically I would write at, well, let me just rewrite that instead of, that would be my answer. We're going to pick up, I don't know if I have enough time to do another problem. So we're going to pick up with one more of these. But let me just, now that we're done writing, let's go back and look at what I did. And then we'll pick up with one of these on Thursday. Folks, I was asked, what is the molarity? Anytime you're asked, what is the molarity? This is your formula. That's what molarity means. That's your formula. So in order to answer the question, what is the molarity? I needed moles of solute and I needed liters of solution. So I looked back at the problem and I identified who was my moles of solute? Who was my liters of solution? We then performed the math necessary to get that solute into the correct unit. So we converted grams of solute into moles of solute using its molar mass. We then did the math to get the volume into the correct unit. So we converted milliliters into liters. Once we had the moles of solute and the volume of solution, that's when we were able to use this equation to solve for the molarity. When dealing with the conversion factors, I rarely use the molar mass to determine sig figs. And the reason is because if I were to use that periodic table, every single element has 6 significant digits. If I use the periodic table I gave you, every element has 4 significant digits. So very, very, very rarely do I actually pay attention to significant digits with respect to molar mass. Because it's really periodic table dependent. So my significant digits came from my original values in the problem. This one had 5 significant digits, this one only had 2. Therefore, I used the 2. And that's where that 0.86 molar came from. Did that, going back over that, did that help some? To clarify the process. We will pick up with one more of these problems, and then we're going to use it as we'll use molarity as a conversion factor. And then we'll deal with dilutions. Dilutions are easy. If you've had biology, you've probably already done the dilution. We just use a slightly different equation. I will see you on Thursday.